everyone. My name is Joseph Wong. I'm a master's student in Nanoengineering. My supervisor is Professor Kesong Yang. We have Dr. Shyue and Tod Pascal on the committee. And today I'm going to be talking about my work for my master's thesis on surface energies of magnetic full heuslers and machine learning analysis of hybrid perovskites. Okay, so here's a broad overview of what I'll be talking about. So first we'll be going over the surface energy of full heuslers. We'll talk about how we did the surface energy calculation, how we created the slab structures, and the results that we got for the surface energies. And in the next project we'll talk about the machine learning analysis of hybrid perovskites. So we'll talk about how we extracted the descriptors, how we designed our machine learning model, and then how we tuned and evaluated that model. And we'll also talk about the results that we got for the effective mass formation energy and the band gap. And then, if we have time, we'll go over some work that I did on 2D hybrid perovskite review. And we'll go over some experimental and theoretical research. Okay, so surface energies of full heuslers. So full heusler is a type of material that has gained a lot of interest recently for applications in memory storage devices as magnetic tunnel junctions. So an example of where you would see this is in something called a magnetoresistive random access memory device, like you see there. And inside of this device is a magnetic tunnel junction. And in this picture we have a Heusler MGO magnetic tunnel junction. So we have the Heusler material as the electrode, as you can see right there, and then MGO as the tunnel barrier. And so this is what a standard full Heusler crystal structure looks like. And what's special about these Heusler alloys is their half metallic band structure. And so what I mean by this is that half of the spin states, the spin down states in this case, they're semiconducting. So you can see that the Fermi energy lies in between the valence band and conduction band, while the other half of the spin states lie within the valence and conduction bands, like this. And so that would be called metallic. And so that's why they're called half metals. It gives us a way to distinguish between the spin up and spin down states in the material. Okay, so here's some advantages of the Heusler MGO magnetic tunnel junction. So there's been a lot of interest in the cobalt-based full Heuslers because they've been shown to be half metals with a very high Curie temperature and a very stable structure. And the Heusler MGO interface has been shown to have a very high tunneling magnetoresistance and perpendicular magnetic anisotropy. And so there's a lot of interest in these particular magnetic tunnel junctions. And why we're interested in the Heusler surfaces. So this Heusler surface has been shown to influence the half metallicity of the material and also influence the spin polarization of the device. The Heusler surfaces also have an effect on the thin film growth conditions. So depending on the surface energy of the substrate and of the thin film, you can get either very smooth layer by layer growth like this, or you can get different types of island growth like you see there. And that can have a big effect on the performance of your device. And so that leads us to the goal of this work, which is to calculate the surface energy of 68 Heusler compounds from first principles. And in doing so, we can determine optimal growth conditions for magnetic tunnel junction synthesis. Okay, so here's what the structure of the full Heusler compound. So the full Heusler follows this formula X2YZ that you see in the top left there. And there's 4 different types of Heusler compounds that exist. So we have regular cubic and inverse cubic, and then we also have regular and inverse tetrahedral. For the purposes of this work, we're only going to look at the regular cubic structure. And we selected 68 stable compounds according to their formation energy. Okay, so if we're looking at the surfaces of these materials, we consider 3 different orientations. So we have the 100, the 110, and the 111 surfaces. And depending on the orientation, we can get a different number of surface terminations. So for example, in the 100 surface, we have two terminations. So we have the X2 and the YZ termination. And what the X2 refers to are these X2 atoms that are exposed to the vacuum. And in the YZ structure, we have the Y and the Z atoms that are exposed to the surface. For the 110 surface, we only have one termination, the X2YZ surface. So if you look at the next layer, you'll see that the composition is the same, so there's only one type of termination that you can get. For the 111 surface, we have three terminations, the X, Y, and Z surfaces. And something that I'd like to point out is that in the 100 and 111 surfaces, these are what's called non-stoichiometric structures, while the 110 is a stoichiometric structure. And what I mean by that is in the stoichiometric structure, we have an integer multiple of the base formula unit within the slab structure. While in the non-stoichiometric structures, we do not have an integer multiple of the base formula unit. And so if you kind of count up the number of atoms, you'll see that in this structure, you can divide it exactly into integer multiple of the base formula, while in these other structures, you cannot do that. So we have the surface energy is equal to the energy of the slab structure minus n times the energy of the bulk structure divided by 2 times the surface area. And the energy of the slab and the energy of the bulk structure, we can calculate that directly from density functional theory. And this n term corresponds to the number of formula units that are in the slab structure. It gets a little bit more complicated in the non-stoichiometric case, but the overall structure of the equation is very similar. The only difference is we have this chemical potential term right here. And this is a term that's used to sort of compensate for atoms that are in excess or lacking in the slab structure compared to n times the bulk formula. So, for example, if we have a slab structure that's X6, Y2, Z2, that would be non-stoichiometric. There's two different ways we can calculate that surface energy. So one is in the X-rich condition, where we have n is equal to 2, and we can also do it in the X-poor condition, where n is equal to 3. So if n is equal to 2, we have a formula of X4, Y2, Z2. And so if you compare that formula to the slab formula, you'll see that there are 2 X atoms that are lacking, and so we have to add 2 times the chemical potential term to compensate for those atoms. Similarly, for the X-poor condition, we have n is equal to 3, and you'll see that in this formula we have 2 in excess of Y and Z, so you have to subtract those chemical potentials from the bulk energy. And these chemical potential terms can be calculated from DFT from the pure bulk structure if we consider it to be rich in those conditions. Okay, so here's a rough flow diagram of how we did our calculations. So we start out with 68 bulk heuslers compounds, and then we use a Python library called PyMatGen to create the slab structures. And we also have a bunch of pure bulk elements to calculate the chemical potential terms. So we do a high throughput density functional theory calculation using a tool called VASP. And then from those calculations, we get the energy terms and the chemical potential terms to plug it into the surface energy equation. And then once we have the surface energies, we can sort them into their corresponding terminations. So the X2, YZ, and all those. Okay, so now we're going to start talking about the results that we got from this calculation. So in this work, for this analysis, we mainly focus on the cobalt-based compounds because that's where we had the most data points, and those have been shown to have very good properties. But before we start talking about that, I'll explain a little bit of what's going on here in these graphs. So we have 2 different graphs. We have one graph for the X-poor condition on the left, and one for the X-rich condition on the right. On the y-axis, we have the surface energies. On the x-axis, we have the Z atoms sorted first by the group number, then by the period number. And if you'll recall, the Z atom is referring to the Z atom in this formula X2YZ. And we separated the group numbers by black dotted lines here. So if you look towards the middle of the x-axis, you'll see aluminum and gallium. Those are both in the same group. We also annotated the Y atom for that data point. And we also have some reference surface energies as the colored lines that you see there. So we have 100 MgO, and we also have the cobalt surface from experiments and also from calculated from density function theory from the Materials Virtual Labs crystallium as a reference point. Okay, so some trends that kind of stand out immediately from these plots. We see that the YZ terminated surface is overall lower than the X2 terminated surface. So those correspond to those red points up there. We also see one interesting trend that we see is that the surface energy will actually decrease with increasing group number and period number of the Z atom. And so this indicates that the surface energy is inversely proportional with the number of valence electrons and the atomic radius of the Z atom. And so you can kind of see that with this trend line that I drew. It's kind of hard to see, but we don't find any trend with the Y atom. Just from other plots that we looked at, we didn't see any trend with the Y atom. We also note that we find a number of compounds with surface energy lower than MgO. So you can see those. There's a few points that are lower than this purple line. Okay, so now for the 110 surface, we see a very similar trend that the surface energy decreases with the group and period number of the Z atom. And so that indicates kind of the same thing, that the surface energy is inversely proportional with the valence electrons, number of valence electrons, and the Z radius. We still don't see any trend with the Y atom, and we also see that the surface energies are a little bit higher compared to the 100 surface. Okay, so for the 111 surface, we have 3 different surface terminations, so you see 3 different colors up there. We still don't see any trend with the Y atom. We see that the surface energies are a little bit higher than the 100 surface. And we still see the same trend of decreasing surface energy with increasing group and period number. And one thing that I thought was interesting to point out here is that we see that the X terminated surface energy approaches the cobalt surface energy when in the X-rich condition. And so you can kind of see that here. And so this kind of suggests that when we have an X-rich condition and we have a surface terminated by a cobalt atom, that is a very similar condition to the bulk cobalt surface. And so we kind of get this very similar surface energy. And we also find a number of compounds with surface energies lower than MgO. Okay, so in conclusion, we found about 22 cobalt-based full Heussler compounds with surface energies lower than MgO. We found that compounds containing the Z atom, containing Z atoms with a higher number of valence electrons and atomic radius will tend to have lower surface energy. And we also see that the X4 condition and terminations without the X atom overall yield lower surface energies. And so that leads us to the 100YZ and 111X terminated compounds to have the lowest surface energies of these materials. Okay, so some future work that I think it might be interesting to look into if we have more time. I think it'd be interesting to look at the relationship between the surface energy, the magnetic anisotropy, and the tunneling magnetoresistance. It might also be interesting to look at the interfacial energy of Heussler MgO, as well as lattice mismatches and strain in that interface, because those are all important when trying to think about how to fabricate the magnetic tunnel junction. Okay, so now I'm going to switch gears here and talk about my next project, which is a machine learning analysis of the hybrid perovskite. So in recent years, there's been a lot of push for renewable energy sources, especially in the solar industry. And one solar material that has gained a lot of interest lately is the hybrid perovskite. And hybrid perovskites are a type of light-absorbing material that have very low cost synthesis requirements and very high power conversion efficiencies. So to kind of illustrate that idea, I have up here a graph of record solar cell efficiencies over time. This is from the National Center for Photovoltaics. And I'd like to point out these yellow-orange circle points that I've circled in red up there. Those correspond to record efficiencies of perovskite devices over time. So you can see that in less than 10 years, the efficiency has skyrocketed almost up to the point of the silicon solar cells that you see up there in blue, which is the current industry standard. And so there's a lot of interest in these materials, but despite the very strong performance in just a very short period of time, there's still a number of challenges that have yet to be addressed. So mainly, the material is intrinsically unstable, especially in the leading perovskite compound. So you see that if you just run the solar cell device after a period of time, you'll see the performance drop significantly in just a short period of time. There's also some concerns about the lead atom, because typically lead is very toxic towards people, and we want to avoid that if possible. So in light of these challenges, there's been a lot of push to search for alternative perovskite materials. And there's a number of different ways that we can do this search. The first one we can think about is the experimental preparation and characterization. So we just go into a lab, buy the material, synthesize it, and characterize it. But the problem with this approach is that it's very expensive and very labor intensive. And so you're kind of limited to only a few compounds at a time when you're doing this approach. Another approach people have looked at is computational simulation and modeling, such as density functional theory. I've used this technique myself in the previous project. However, even with this technique, even though you can simulate potentially thousands of compounds at a time, just by the nature of these calculations, you're often limited by computational resources. And so that leads us to the third approach, which is machine learning modeling. And machine learning essentially uses data that has been previously generated to make predictions on materials that it has never seen before. And this approach does sacrifice a little bit of accuracy compared to the other approaches, but it greatly improves the technique speed and throughput. And so that's the technique we use in this project. Okay, so the advantage of machine learning is that you're able to use data that has been previously generated to explore a very high dimensional feature space, and you're able to identify trends in those features. So you can use a variety of descriptors to predict your target variables. So these could be things like bond angle, atomic composition, and different things like that. In this work, we're mainly using the compositional features, which are features that are more readily available from your data. So in this work, we use primarily compositional features for machine learning prediction of the formation energy, the band gap, and the effective masses. Okay, so here's a flow diagram of how this process works. So we start out with 1,902 data points. We can divide that data into 208 single perovskites and 1694 double perovskites. We can extract the descriptors using a tool called MapMiner, and then we can train the machine learning model from this data using some machine learning libraries like scikit-learn and XGBoost. And we can use those models to make predictions on our target variables. Okay, so here's a list of the composition-based descriptors that we looked at. So all these descriptors that you see up here, you can derive that just straight up from the composition of your material. So these are things like the atomic number, the valence electrons, or electronegativity. Okay, so here's a rough diagram of our machine learning model. So in this work, we use a technique called a meta-ensemble. And so basically how this works is we start out with our input data on the left there, and we feed that to a base layer which contains a series of machine learning models, and each of these models takes in all of the input data and makes its own prediction on the target variable. So in this case, we could be thinking about the band gap, and each of these base models makes its own prediction on what it thinks the band gap is. And in this model, we pass those predictions from the base model to the meta layer. And the meta layer has some models that take the inputs, the predictions from the base layer as inputs for the training and prediction of each machine learning model. And so once we pass that to the meta layer makes predictions of its own on what it thinks the band gap is, and then we can take the average of those predictions to get a final prediction of what the target variable is. So that could be the band gap, or formation energy, or effective mass. Okay, so if you're interested, here's a list of the machine learning models that we use. So most of these are implemented in scikit-learn, and we also use XGBoost for one of the meta layer models. Okay, so now I'm going to talk about how we tuned the hyperparameters. So what I mean by hyperparameters is a list of features that are used in the machine learning model to essentially do its training on the data. So these are things like the max depth of our model, the learning rate, the number of estimators, and different things like that. And there's two different ways that we use to do this hyperparameter tuning. So one is a grid search technique, and another one that we use is a Bayesian optimization approach. So in the grid search technique, basically what you're doing is you're testing out every possible combination of parameters within your feature search space. And so this is very good because you can find a global minimum, like the perfect combination of hyperparameters that allow you to get the best results. However, this can be very computationally expensive, especially if you're trying to use a very fine grid. And so in this work, we only use this approach for models with a low dimensional search space. So things with like only a very few number of hyperparameters. The other approach that we looked at is the Bayesian optimization approach. And we use a library called HyperOpt for that. And this technique is kind of similar to a gradient descent approach. So basically you're using the results of previous calculations, previous test trials to guide where you're going to do your next searches. So basically in this approach, you drastically reduce the computational resources required in this calculation because you're using some kind of guided approach to do your testing. However, the problem that can happen sometimes is you can reach a local minimum rather than the global minimum. And so we use this technique for models with a very high dimensional search space. Okay, so here's how we evaluated our model. So we used something called the root mean squared error. So you can see that in that equation up there. And basically what this is telling us is it's a measure of how far our model deviates from the true values. And so ideally we want to have a root mean squared error of 0, but that's not practical. Usually we have some kind of value for that. And we use something called k-fold cross-validation to avoid overfitting. So when we do machine learning, we have to divide our data into a set of training data, which the machine learning model digests and uses it to identify its parameters to do the fitting. And we also have to divide it into a set of test data so that we can evaluate how well our model does on data it's never seen before. And in k-fold cross-validation, basically we're splitting up the data into a number of folds, and in each fold we set aside a different index of test data and training data to train and evaluate our model. And so in this case we're using 4 different folds, and in each fold we have a different set of test data. And so this is good for avoiding, or just to avoid any overfitting in our data, or in our machine learning model. Okay, so here's how the overall flow process of how we did the validation approach. So we start out with our input data, and we can split that data into 80% training data and 20% validation data. We can perform k-folds cross-validation on the training data, select the best iteration model from the k-folds, and then we finally check the accuracy of that best model with the 20% validation data to get final evaluation of the model accuracy. Okay, so now we're going to talk about the results that we got from this. And one of the first things that we want to look at is formation energy. And before we get into the results of how well our model did, we'll look at the feature importances. So this is a bar plot of the relative importance of each feature. So we can see here in this graph, there's one feature that stands out above the rest as being important for the formation energy, and that is the ionic character. In the case of double perovskites, this is the average ionic character. In single perovskites, this is the max ionic character. And we see that from these results, we can get a very good model, very accurate predictions. So we have a very low root mean squared error, less than 0.1. And in these plots, we have the real values plotted against the predicted values. And in the best case scenario, we would have all the points lie on that dotted line up there. But typically, we'll see a little bit of deviation. So in this case, we see that most of the points lie along this dotted line here, indicating that there's a very good fit with our model. And we also see the red points, the test data, plotted against the blue points, the training data. And we see that there's not too much difference in terms of spread between the red and the blue points. And so we can conclude that there's a very little overfitting going on with our model. So yeah. Question?
The units are in EV per atom?
Yes, in this case.
So your root mean square error is still 50 to 90 MeV per atom. That's actually pretty large. I mean, it looks like it's a straight line, but the spread is quite large.
So, okay, so you're saying the root mean squared error is actually the milli-electron volts.
No, it's 90 MeV. It's pretty large.
Okay, yeah.
Or especially when you're talking about per atom basis.
Okay, all right, that's noted. Okay, so now we'll talk about the band gaps, the band gap analysis. So, unlike the formation energy, there's not really one feature that kind of stands out from the rest. There's rather a couple of features that are kind of important in the prediction of the band gap. So we looked at the PBE and HSC band gap. So what we'll see here is that in the double perovskites, we find that the transition metal fraction and the d-valence electrons are important for predicting the band gap. And so that is indicating that the transition metal selection is very important in determining the band gap of the material. We also find that the ionic character is important in all cases, kind of similar to the formation energy. And we also find that the electronegativity difference is important only in the single perovskites. Okay, so here's our results for the band gap results. So we see that there's a little bit more spread compared to the formation energy. We have a little bit higher root mean squared error. So we don't have as good as a high accuracy, but still have decent results. We don't really see too much overfitting. The red points kind of a very similar spread as the blue points. And we also see that the results of the double perovskites are a little bit more accurate than single perovskites. And this could be just because there's more training data available for the double perovskites. We also see that the PBE band gap is a little bit more accurate than the HSE band gap. Okay, so now I'm going to talk about the electron and hole effective mass results. So what you see in these plots right here is that there's even less of a bias towards one particular feature, but rather there's a kind of a big set of features that are important in predicting the effective mass. So these are things like electronegativity features. We also see the oxidation state, the number of d-valence, the sp and d-valence electrons. And we also see some structural features like the tolerance factor and the ratio between different atoms in the system. Or the ratio of radii of atoms in the system. Okay, so here's our results for the effective mass. So what you'll see that kind of stands out immediately in these plots is that there's a lot more spread compared to the formation energy and the band gap. And that also shows itself in the larger root mean squared error values. We also see fewer data points for higher effective mass values. So the model may not perform very well for larger effective masses. And we also see a greater dependence. We suspect that there could be a greater dependence on other unused features that we have not considered in the study. So things like bond angles or bond distances or maybe space group. Yeah, question?
Yeah, sorry, when you're plotting training, is that the labels, the ground truth, or is that the predictions on the training set from the model when you're plotting training?
Okay, so in these plots, we plotted the predictions from the machine learning model on both the training and the validation set. So the predictions on the training data is in the blue, and the predictions on the test set are in red. And then we plot it against the true values.
Okay, thank you.
Yeah.
I think he's asking whether your ground truth is the x-axis or the y-axis.
So I believe it's in the x-axis, but it doesn't really matter. If you flip the axis, you'll get a pretty much the same plot.
Yeah.
Okay. So in conclusion, we looked at the formation energy, the band gap, and the effective masses. So we determined that the ionic character is very important in both single and double perovskites, and we thought we had a very good model accuracy, but might need to look into that again. So we also looked at the band gap. We find that electronegativity is very important in single perovskites, and we find that transition metal fraction and d-valence electrons, or in other words, the selection of the transition metal is very important in double perovskites. We also find that the ionic character is important in both single and double perovskites. We get decent accuracy. We also find that the PDE band gap is a little bit more accurate than the HSE band gap. For the effective mass results, we find electronegativity, oxidation state, and fraction of SPD valence electrons and the tolerance factor as important features for both single and double perovskites. But we find that there's a little bit of a lower accuracy of the model compared to formation energy and band gap. Okay, so in future works, I think there's a number of different directions we could go if we had more time to work on this. So one is so all this work is sort of the preliminary work to design the machine learning model. In future works, we would like to apply that model to explore the chemical space. So depending on the number of atoms and cations that we're considering here, we could get potentially hundreds of thousands of perovskite materials that we could study with this model. And we could also think about including a structural template to artificially generate structural descriptors to boost the model accuracy. And we could also think about creating a database of hybrid perovskite materials using this model. And we could also think about implementing this machine learning model as a tool in our group's software library that's currently in development called AIMS, to quickly make predictions of band gap, formation energy, and effective masses just from the composition. Okay, so I think we have some time. We'll talk about some work that I did on 2D hybrid perovskites. So 2D hybrid perovskites are a type of perovskite material that follows the formula that you see right there, R2MAMX. And the main difference between the 2D and 3D perovskites is this R molecule right here. And this R molecule corresponds to this very large organic group that you see here. And because of the large size of these organic molecule, the steric hindrance causes the inorganic layers to split into two-dimensional layers like that. And depending on your synthesis conditions, you can also control the dimensionality, which corresponds to the number of inorganic layers between these organic molecules. And so the advantages, why people are interested in these 2D perovskites, is that the synthesis approach is very simple. For most cases, you can just use a simple one-step fabrication approach to get very smooth, uniform thin films. They also have much higher stability compared to the 3D perovskites. We also see that it's very easy to control the band gap just by controlling the dimensionality. And we also find that there's a much stronger exciton binding energy, which leads to very interesting light emission properties. There are some disadvantages of these materials. the power conversion efficiency is much lower compared to 3D perovskites. So from looking at the literature, we find that the record efficiency is about 12%, compared to a 24% for 3D perovskites. We also see typically they have a larger band gap and charge carrier anisotropy, which is not very good for solar cell performance. Okay, so now we're going to start talking about some experimental work that's been done on these materials. So one thing that a lot of studies have shown is band gap control from the dimensionality. So depending on your synthesis route, you can control the number of inorganic layers between the organic cations. And by controlling the dimensionality, you can control the exact band gap that you'll get. So you see in this plot right here, these are absorbance plots. And so you'll see that depending on the n value, you can get different absorbance values corresponding to a different band gap. And so in that way, you can easily control the band gap of these materials. We also see that there's some very interesting light emission properties of these materials. So one of the properties that I thought was very interesting is white light emission. So typically, white light emission in just one material is very hard to achieve. Typically, you have to make a combination of different materials to get that white light. But in 2D perovskites, some of the 2D perovskites, you can get white light emission just from the one material, like you see there. We also see that a lot of studies have shown that the stability of these perovskite materials is much higher compared to the 3D counterparts. So you see these plots are the power conversion efficiency over time. And the 2D perovskites correspond to those red points, while the 3D perovskites correspond to those blue points. And you'll see in all these graphs, the power conversion efficiency is pretty stable, especially in the encapsulated condition, while for 3D perovskites it just drops off very quickly. And so that kind of shows that these 2D perovskites are much more stable compared to 3D perovskites. Okay, so now I'm going to talk about some theoretical research. So generally, the theoretical research kind of confirms the experimental research. Many studies have shown that the tunable band gap type of idea with increasing or decreasing dimensionality. So in this case, we have butyl ammonium, methyl ammonium, and germanium iodide 2D perovskite. And what we see here in these plots, so these are different band structures of the perovskite material depending on the n value. So I believe if you go from left to right, these are increasing n values. And what you see here is that the valence band and the conduction band tend to get closer as you increase the n value. And what we also notice is that the band structures are primarily derived from the germanium and iodine atomic orbitals, indicating that only the inorganic components are conducting or involved in the charge carrier mobilities. Okay, so many studies have also shown that the charge mobility is very anisotropic. So we see that in the gamma X and RT directions, or the directions that go out of the inorganic plane, those tend to have flat bands that you can kind of see up there, those flat bands. And those are indicating that there's a very almost infinite effective mass in those directions. And that means that the charge carriers cannot move out of the inorganic planes, and they're kind of confined to this 2D plane of inorganic materials. We also see that some studies have shown that the formation energy is much lower from their calculations. So you see that as you decrease the n value from infinity down to n equals 1, the formation energy gets much lower, indicating that it's more stable. All right, so just a summary of what I talked about. So there's much higher stability relative to 3D counterparts. There's some interesting light emission properties, like white light emission, because of the high exciton binding energy. There's highly tunable band gaps, but in exchange for all that, we have a lower power conversion efficiency. And this is due to charge carrier anisotropy and a large band gap. So now I'm going to very quickly talk about some other work that I did. So I did some work on the configurational entropy of some thermal barrier coating materials. So in this work, by analyzing the configurational entropy, we identified a few ground states to do the defect segregation study in this work. I also did some documentation of AIMSGB, which is a Python library for systematic generation of the grain boundaries. I uploaded that up to our website, aimsgb.org, and wrote a little manuscript, which is in preparation right now. Okay, so here's a list of publications that I was involved with. 3 of them have been published already, and 4 of them are in preparation or getting ready to be submitted. Okay, so with that, I'll conclude my talk by acknowledging a number of people. So the first person I'd like to acknowledge is Professor Kesong Yang. He's my supervisor throughout these few years of research. I'm very grateful for his mentorship and guidance and being able to help me with my research and to develop my critical thinking and my writing skills. I'd also like to thank my committee members who have been very gracious to show up today to be on the committee, Dr. Shyue and Dr. Tod Pascal. And I'd also like to thank my group members who have helped me out in my research. So Dr. Safdar Nazir, Dr. Mazir Beitosh, Dr. Jenli Chang, Yuheng Li, Paul Ju, and Kesong Yang. I'd also like to thank some family and friends, my parents, Walter and Nancy Wong, my lion dance team, Southern Sea Dragon Lion Dance Association, and also my church, Lighthouse Bible Church. And also these funding resources, NSF grants, Office of Naval Research grants. And with that, I'll be done talking and I'll take any questions.
Before we have more questions, I would like to give more introduction about Joseph Wong. Joseph actually is an undergraduate student at UC San Diego, and he has worked with me since he's a sophomore year, I think. So, and he's in the program of the 4+1, which means 4 years undergraduate study at UCSD and plus only 1 year master. So this is his last year of of course, his first year or the last year of the master degree. So he's only spent 1 year on this master degree. That is also a very useful program for many students at UC San Diego. And all right, things. Do we have some more questions from our students' audience? Yeah, please.
For your work on the heuslers surfaces, so it's well known that for the 001 surface of half heuslers, that they have these reconstructions. Have you considered that for your full heuslers surfaces, especially since you're working on the X equals cobalt structures?
So here's surface reconstruction. Are you talking about if we did structural relaxations? Because all these are structurally optimized, but we didn't really consider any sort of structural reordering of the surface. We just kind of took them as is, like those structures that you saw up there. Those were the structures that we used in our calculations. Yeah.
In your machine learning work, you mentioned you use a base model, meta model approach. Could you comment some on why you chose that approach as opposed to having all of the models maybe linearly, as opposed to feeding the outputs of the base models, and I assume the features again into the meta models? Because you already have predictions, and then you're just taking the predictions and sending them to a second set of meta models, and then you're just doing weighted, averages at the end of the meta models. So why that structure over like a linear column structure?
Okay, so the reason why we use a type of meta model is that it's been shown to increase the accuracy compared to just using the individual models. And we actually did tests on whether we're using the meta model only on the predictions of the base layer or also including all the features from the input data. So in both approaches, we got very similar results. So we just decided on the average, which was a little bit more consistent across these tests.